Tonight, we are going to dismantle a picture that has been sitting in your mind since childhood. A picture so tidy, so familiar, so comfortable that you have probably never questioned it. You have seen it in textbooks. You have seen it on posters taped to classroom walls. You have seen it on the covers of children's books and in the opening seconds of 1,000 documentaries. A yellow sun in the center. 8 neat little planets drawn in perfect concentric circles around it. Mercury, Venus, Earth, Mars. Then a scattering of asteroids. Then Jupiter, Saturn, Uranus, Neptune. And beyond them a black background, empty, silent, nothing. That is the solar system we were told. That is our home. That is where we live. But tonight, we are going to ask a question so strange, so quietly unsettling, that it might keep you awake long after this video ends. A question that most people never think to ask, because the answer feels obvious, and because the answer, as it turns out, is wrong. Where does our solar system actually end? Not where the last planet orbits, not where the light of the sun fades, not where the diagrams stop drawing rings, but truly, physically, measurably. Where does the influence of our star surrender to the galaxy beyond? And when it does surrender, what waits on the other side? For most of human history, we could only guess. We stared at the night sky and imagined the stars as tiny holes punched in a great black dome. We imagined the space between them as empty, as nothing, as void. Even as our science advanced, even as we launched telescopes and mapped the planets, even as we photographed distant galaxies, the region just beyond our own cosmic neighborhood remained a blank space on the map. Terra incognita, the place we could not reach. And then in the late 1970s, we did something extraordinary. We built 2 small spacecraft, no larger than a subcompact car, packed them with instruments and threw them outward. Not toward another world. Not toward a specific target, but outward in the truest sense of the word. Outward toward the edge of everything we call home. And nearly half a century later, those 2 spacecraft, Voyager 1 and Voyager 2, did something no human-made object had ever done before. They crossed a boundary we did not fully understand. A boundary we had only theorized. A boundary that separates the domain of our sun from the vast, cold, ancient territory of the galaxy itself. And what they found there at that boundary, and what NASA continues to piece together from their signals to this very night, has quietly rewritten our understanding of what our solar system actually is. Where it ends, what surrounds it, and what our place in the cosmos really means. Before we go any further, if you find this kind of slow, deep, contemplative exploration fascinating, the kind of story you can sink into on a long, quiet night, a small like or a quick subscribe genuinely helps this channel keep making these journeys. It is a small thing for you. It is a huge thing for us. Now settle in, let yourself get comfortable, and let us begin. You see, the picture you grew up with, that flat, tidy diagram with the sun and the 8 orbiting planets, is not just simplified. It is misleading. It is misleading in ways that matter. It is misleading in ways that hide the true nature of where we live. Because our solar system is not a set of rings on a black background. It is not a collection of worlds floating in emptiness. It is not a diagram at all. Our solar system is a bubble, an immense, invisible, magnetic bubble. Blown outward from our star, expanding in every direction at once, pushing back against the pressure of the galaxy. A bubble that shelters us, a bubble that shapes us, a bubble that we live inside without ever seeing its walls. And beyond that bubble, at its outermost edge, there is not emptiness. There is something else, something older, something that has been there since long before our sun existed, something that our two brave spacecraft, drifting for decades in silence, finally reached and touched and measured. And what they measured was not what anyone expected. Take a breath for a moment. Let that idea settle, because to truly appreciate what NASA has found beyond the heliosphere, beyond that bubble, you have to first let go of the diagram, the flat one, the tidy one, the one with the little concentric rings. It is not that the diagram is a lie exactly. It is that it is a shadow, a thin, two-dimensional sketch of a place so vast, so strange, and so alive with invisible forces that the diagram cannot begin to hold it. Think of it this way. Imagine you have lived your entire life inside a house and someone hands you a floor plan, a simple line drawing, rooms as rectangles, doors as gaps, and you look at that floor plan and you nod and you say, "Yes, this is my home." But of course, the floor plan is not the home. The home has light coming through the windows. The home has warmth in winter and coolness in summer. The home has walls that hum quietly with electricity, and floors that creak in the night, and a roof that keeps the weather out. The floor plan tells you nothing of the walls. The floor plan does not even mention that there is a roof. The diagram of the solar system you grew up with is the floor plan. It shows you the rooms. It does not show you the walls. It does not show you the roof. The walls exist. The roof exists. And beyond them, there is a whole world you have never been told about. That whole world begins at a place called the heliopause, a word most people have never heard spoken aloud, a word that describes the outer skin of our star's influence, the boundary where the sun's endless outward wind, a stream of charged particles traveling at hundreds of kilometers per second, finally, after a journey of many billions of kilometers, meets a pressure it cannot push through. The pressure of the galaxy. The pressure of what lies between the stars. And when those two pressures meet, they do not simply cancel each other out. They collide, they churn, they heat. They tangle magnetic fields into knots. They create a region of turbulence and mystery, a skin, a shell, a frontier. For most of the 20th century, this frontier was purely theoretical. Scientists calculated that it must exist. They gave it a name. They drew rough sketches of what it might look like, but no one had ever been there. No one had ever measured it. It was, in every practical sense, a rumor about the edge of our home. And then Voyager 1 crossed it. On the 25th of August, 2012, at a distance of roughly 18 billion kilometers from the Sun, a distance so vast that the light from our star takes more than 17 hours to reach it, Voyager 1's instruments recorded something strange. The particles around it changed. The magnetic field around it shifted. The cosmic rays flooding in from deep space suddenly surged, while the particles from our own sun quietly faded. It was as if the spacecraft had stepped through a door and closed it behind her. She had left the bubble. She had entered the galaxy. 6 years later, in November of 2018, her twin, Voyager 2, made the same crossing, from a different location, through a slightly different door, and her measurements were slightly different, which told scientists something they had not expected. The wall of our bubble is not smooth. The wall of our bubble is not uniform. The wall of our bubble has texture and structure and surprises, and that is where our story truly begins tonight. Because everything you are about to hear, everything about the shape of our home, the fire at its edges, the ribbon that should not exist, the cloud we are drifting through, and the vast dark chambers of the galaxy waiting just beyond. All of it comes from the whispers of those two small ancient spacecraft, and from the missions we have sent up in the years since to try to understand what they found. We have not even gotten to the strangest part yet, not by a long stretch. What lies just beyond the heliopause is stranger than anyone predicted, and what wraps around it is stranger still. And what surrounds all of that, holding our little bubble like a bead in a much larger structure, is something so vast and so quiet that, when you learn about it, you may never look up at the night sky the same way again. But first, before we go outward, we have to understand exactly what this bubble is, how it formed, why it exists, and why, without it, none of us would be here at all. So before we drift on together, take a moment and ask yourself this. When you were a child, when you first looked up at the stars, or when you first saw that little diagram of the solar system in a book, what did you think was between the planets? What did you imagine filled the space between us and the next star? And now that you know that space is not empty at all, but full of invisible currents and pressures and boundaries, does it change how you feel about the sky above your window tonight? Take a moment. Sit with that question. And when you are ready, we will step outward together, into the bubble we live inside, and toward the edge we did not know was there. To understand what NASA found beyond the heliosphere, you first have to understand the heliosphere itself. And to understand the heliosphere, you have to understand something almost no one thinks about, something happening every second of every day, right now, above your head, without pause, without rest, without any indication to your senses that it is happening at all. Our sun is bleeding, not violently, not painfully, but constantly. From every point on its surface, in every direction at once, our star is losing itself to space, a steady, silent, unstoppable outward flow of its own substance. Not light, not warmth, something else, something more physical, a wind. Astronomers call it the solar wind. And the name is deceptively gentle, because this wind is not made of air. It is made of the very particles that compose the sun itself. Protons, electrons, the stripped-down nuclei of atoms. Charged pieces of matter, torn free from the sun's atmosphere by heat so extreme that no atom can hold itself together. And these particles do not simply drift away. They are hurled outward, screaming outward, at speeds of somewhere between 300 and 800 kilometers per second. Faster than any bullet, faster than any rocket, fast enough to cross the distance from the sun to the Earth in just a few days. And this wind never stops. It has been blowing since the sun ignited 4.5 billion years ago. It will keep blowing until the sun dies. And in every moment of every one of those years, it has been pushing outward, expanding, filling the space around our star with a thin, invisible, electrically charged breath. Now here is the strange part. Here is the part that changes everything. That wind creates a bubble, because as the solar wind rushes outward, it pushes against whatever is out there. And what is out there, the space between the stars, is not empty. It is filled with its own thin material, its own particles, its own magnetic fields, its own pressure. This is what astronomers call the interstellar medium, the stuff between the stars, and the interstellar medium pushes back. For most of the journey outward, the solar wind wins. It is faster, denser, more energetic. It carves a cavity in the galaxy around us. It sweeps the interstellar medium aside like a river cutting through soft earth. But the further the wind travels from its source, the weaker it becomes. It thins. It slows. And at some point, at some vast distance from the sun, the wind finally weakens enough that the interstellar medium can push back with equal force. And where those two forces meet, they carve out a boundary. That entire region, the space carved out by the solar wind, the domain where our sun's breath still holds sway against the pressure of the galaxy, that entire region is called the heliosphere. From the Greek helios meaning sun, sphere meaning bubble, the sun's bubble. And it is enormous. Try for a moment to picture the scale. The Earth orbits the sun at a distance of about 150 million kilometers. Astronomers call this distance 1 astronomical unit, or 1 AU. It is the yardstick of our solar neighborhood. Neptune, the outermost of the classical planets, orbits at about 30 AU. Pluto, at its most distant, wanders out to nearly 50. But the edge of the heliosphere, the outer skin of our bubble, sits at somewhere between 120 and 150 AU from the sun. That is roughly 4 times farther out than Neptune. That is a bubble so large that if you were to shrink Neptune's entire orbit down to the size of a dinner plate, the outer edge of the heliosphere would still be somewhere out beyond the edge of your kitchen table. And within that bubble, everything you know exists. Every planet, every moon, every asteroid, every comet you have ever seen streak across the night sky, every spacecraft ever launched, every human being who has ever lived, all of it floating inside this single, invisible, magnetic breath of our star. Let that sink in for a moment. You have never left the bubble. No one you know has ever left the bubble. No one in all of human history has ever left the bubble. In a very real, very physical sense, the heliosphere is the largest thing you have ever been inside of. But the heliosphere is not a simple sphere, and it is not just a bubble in the way you might blow a soap bubble from a wand. It has layers. It has structure. It has regions with their own names, their own personalities, their own strange behaviors. Closest in, extending from the sun outward for many billions of kilometers, is the region where the solar wind flows freely, at full speed. This is the domain of the planets. This is where we live. This is the calm interior of the bubble, if you can call anything traveling at hundreds of kilometers per second calm. But as the wind travels outward, past Neptune, past the Kuiper belt where Pluto orbits, past the frozen worlds and drifting comet nuclei of the outer solar system, it eventually reaches a place where it can no longer maintain its speed against the pressure ahead of it. And at that place something dramatic happens. The wind slams on its brakes, not gradually, suddenly, violently. It drops from supersonic speed to subsonic speed almost instantly. It piles up on itself, it heats up, it thickens. Astronomers call this the termination shock. The termination shock is not a wall. It is more like a shock wave, the same kind of shock wave that forms in front of a jet breaking the sound barrier. But this shock wave is spherical, wrapped around our entire solar system, sitting somewhere between 80 and 100 AU from the Sun. Voyager 1 crossed the termination shock in 2004. Voyager 2 crossed it in 2007. Both spacecraft transmitted the event back to Earth, and both showed us that, yes, the theory was right. There is a place, out in the darkness beyond the planets, where the solar wind loses its speed and begins to pile up. Beyond the termination shock lies a region called the Heliosphere. This is the thick, turbulent outer layer of our bubble. It is where the slowed-down solar wind churns and swirls, mixing with itself, building up pressure, before finally reaching the true outer skin. The Heliosphere is not a thin membrane. It is deep. Voyager 1 spent nearly a full decade drifting through it before reaching the other side. Think about that. A spacecraft moving at nearly 17 kilometers per second, faster than almost anything humanity has ever launched, took 10 years to cross just the outer layer of our bubble. 10 years of relentless motion, and still she was inside our home. And then, finally, at the outermost edge of the Heliosphere, lies the heliopause. This is the true boundary. This is the skin of the bubble. This is where the pressure of the sun's wind and the pressure of the galaxy balance exactly. Push on this side of it and you are still inside our solar system's magnetic domain. Push on the other side and you are in the galaxy. The heliopause is not perfectly round. It is not perfectly smooth. It bulges in some places and contracts in others. It ripples. It shifts. When the sun becomes more active, when it flares and produces bursts of stronger wind, the heliopause is pushed slightly outward. When the sun quiets, the heliopause creeps back in. Our bubble breathes. Slowly, over years and decades, in and out, expanding and contracting in response to the beating of our star's heart. And here is why all of this matters. Here is why the heliosphere is not just an interesting piece of astronomy trivia. Here is why it matters to you personally tonight. The heliosphere is a shield. Beyond our bubble, the galaxy is filled with high-energy particles, cosmic rays. Fragments of atoms accelerated to nearly the speed of light by distant supernovae, by the magnetic storms of other stars, by processes we still do not fully understand. These particles are dangerous. They damage DNA. They scramble electronics. They pose one of the greatest hazards to any long-term voyage away from Earth, and the heliosphere deflects most of them. It acts like a magnetic umbrella, holding much of that cosmic rain away from the inner solar system, allowing life on Earth to develop and thrive relatively unbombarded. Without the heliosphere, the biosphere of Earth would still exist. Our atmosphere and our own magnetic field provide additional layers of protection. But the deep patterns of cosmic radiation, the slow drip of genetic damage across geological time, the very conditions under which complex life evolved on this planet, all of those have been shaped, quietly, by the invisible shield of our sun's breath. We are, in the deepest sense, children of the bubble, sheltered by it, formed by it, utterly dependent on it, though we have only known of its existence for a single human lifetime. Now here is a question worth pausing on. Every time you have felt the sunlight on your skin, you were feeling the innermost expression of the same force that reaches out and carves this bubble around us. The same star, the same outward push, just, in your case, in the form of light rather than wind. And it made me wonder, when you think about our sun now, knowing that its influence extends far, far beyond what you can see, does it feel more powerful to you? Or does it feel more fragile, this single flickering star, holding a bubble of protection around a small blue world? Sit with that, because in a moment, we are going to follow two spacecraft to the very edge of that bubble. Two spacecraft that spent nearly half a century drifting outward through this vast, layered, invisible cathedral of our sun. Two spacecraft that are, right now, on the other side. And what they sent back to us in the final years of their journey is where the true strangeness begins. In the summer of 1977, on a warm morning at Cape Canaveral, two rockets stood on their launch pads waiting to be lit. They were not carrying astronauts. They were not aimed at the moon or Mars or any specific destination that most people would have recognized. They were carrying two small spacecraft, each weighing less than a compact car, each packed with instruments and cameras and a strange golden record etched with the sounds of Earth. And they were being sent, quite literally, outward. Outward toward the giant planets. Outward toward the darkness beyond them. Outward on a journey that no one at the time truly believed would last as long as it has. The mission was called Voyager. Two spacecraft, Voyager 1 and Voyager 2, built by hand in the 1970s with the technology of that era. Computers with less processing power than a modern greeting card that plays a tune when you open it. Memory measured in kilobytes. Cameras that had to be pointed by turning the entire spacecraft with tiny bursts of thruster fuel. And yet these two small, primitive, unbelievably clever machines were about to become the longest-lived, farthest-traveling, most remote emissaries the human species has ever produced. Voyager 2 launched first, on the 20th of August, 1977. Voyager 1 followed 16 days later on the 5th of September. Their names, as it turned out, would be misleading. Voyager 1 was launched second, but on a faster trajectory, and would eventually overtake her sister to become the more distant of the two. Their original mission was almost quaint by today's standards. They were supposed to fly past Jupiter and then Saturn, and then, if their instruments were still working, send back what pictures they could of those alien worlds. That was it. That was the plan. A grand tour of the outer planets. A few years of exploration. Then silence. But Voyager 2 did something extraordinary. She kept going. She flew past Jupiter in 1979. She flew past Saturn in 1981. She flew past Uranus in 1986, becoming the first and still the only spacecraft in history ever to visit that pale blue world. And then in 1989, she flew past Neptune, giving humanity its first close-up view of that distant, storm-racked, deep blue giant. And through all of this, both spacecraft kept their instruments running. They kept their radios pointed toward home. They kept whispering back across the widening gulf between us and them. And then, once the planets were behind them, they entered a phase of the mission that had never been formally planned. A phase that the original engineers, working in the 1970s, had scarcely dared to hope for. A phase that came to be known simply as the Interstellar mission, because both spacecraft, having done their planetary work, were still moving, still traveling outward at more than 15 kilometers per second, still leaving the solar system behind. And no one at the beginning knew exactly when or where or how they would cross the outer edge of the heliosphere. The theoretical models gave rough estimates, perhaps 100 astronomical units from the Sun, perhaps 120, perhaps 150. The estimates disagreed. And the only way to truly know was to keep listening, keep tracking, keep watching for the signs. For years, the Voyagers drifted through the outer regions of the solar system, sending back gradually thinning trickles of data. The particle detectors kept counting. The magnetometers kept measuring the direction of the magnetic field around them. The plasma wave instruments kept listening for the faint hiss of charged gas vibrating around the spacecraft. And slowly, subtly, patiently, the character of that data began to change. The first hint that something was coming came in 2004. Voyager 1's instruments detected a sudden slowdown in the solar wind around her. The stream of particles from the Sun, which had been rushing past her at hundreds of kilometers per second for decades, abruptly dropped in speed. The magnetic field jumped in strength. The number of energetic particles around the spacecraft spiked. She had crossed the termination shock. She had entered the Heliosphere. She had officially begun the final approach to the outer skin of our bubble. Voyager 2 crossed the termination shock 3 years later in 2007 at a slightly different distance from the Sun. And already, that difference was telling us something. The heliosphere was not symmetrical. Its outer regions were not shaped like a perfect ball. There was structure out there. There were asymmetries. The bubble had a shape more complex than anyone had drawn. And then came the long, slow drift through the Heliosphere. That thick, turbulent outer layer where the slowed solar wind churns and piles up before meeting the true edge. Voyager 1 spent almost 8 years traveling through this region. 8 years of steady, uneventful, patient outward motion. And during that time, mission scientists back on Earth watched their instruments for the signs of the next great crossing. They knew, roughly, what those signs would look like. When Voyager 1 finally crossed the heliopause, they expected three things to happen. First, the cosmic rays from deep space, the high-energy particles from distant supernovae that had been partially blocked by the heliosphere for the spacecraft's entire journey. Those cosmic ray counts should surge upward. Second, the flow of low-energy particles from our own sun should drop, ideally to nothing. And third, the direction of the magnetic field around the spacecraft should shift, because on the other side of the heliopause, the magnetic field belongs to the galaxy, not to the sun. Two of those three signals arrived, dramatically, in the summer of 2012. On the 25th of August of that year, Voyager 1, then at a distance of about 122 AU from the Sun, sent back readings showing that her cosmic ray counts had jumped by more than 9% almost overnight. And her low-energy particle counts, the ones from the Sun, had collapsed to nearly zero. Two of the three predicted signatures had appeared, sharp and clear. But the third signature, the shift in magnetic field direction, did not arrive. The magnetic field around Voyager 1 stayed pointed in the same direction it had been pointing for years. And this puzzled scientists for months. Had she crossed the boundary or hadn't she? It took another full year of careful analysis before the mission team was ready to announce it publicly. Voyager 1 had, in fact, crossed the heliopause on that day in August 2012. The magnetic field had not shifted because, apparently, the field on the other side of the boundary happened to be aligned in nearly the same direction as our own. A quiet coincidence. A magnetic handshake, but everything else pointed to the same conclusion. She was out. She was, for the first time in human history, a piece of humanity that had crossed into interstellar space. 6 years and 3 months later, on the 5th of November, 2018, Voyager 2 crossed her own heliopause. At a distance of almost the same, roughly 119 AU from the Sun, but on a completely different heading, in a completely different region of the bubble's outer skin. And her data was different. Her data was, in some ways, cleaner. She had a working plasma instrument that Voyager 1 had lost decades earlier. And that plasma instrument gave scientists something they had never had before: a direct measurement of the interstellar medium itself, taken from inside it in real time by a functioning instrument built by human hands. And what did that instrument reveal? The plasma out there, the thin gas of charged particles between the stars, was more than 40 times denser than the plasma had been just inside the heliopause. 40 times. Think about that. On one side of the boundary, thin and sparse. On the other side, dramatically thicker. Not empty, not nothing. Something substantial. Something that had been waiting for us to notice it. Right now, as you listen to this, both Voyagers are still transmitting. Both are still moving outward. Both are still, however faintly, whispering back to Earth. Voyager 1 is now more than 167 AU from the Sun. Voyager 2 is more than 139. The signals from Voyager 1, traveling at the speed of light, take more than 23 hours to reach us. When she transmits something today, We do not hear it until tomorrow. Her voice is old by the time it arrives, and her voice is faint. Her radio transmitter puts out about 22 watts of power, less than a household light bulb. And by the time that signal reaches Earth, it has spread out across such a vast distance that the amount of energy actually captured by our antennas is measured in fractions of an attowatt, less than a billionth of a watt. And yet we hear her. We still hear her, every day, faint, patient, persistent, but she is dying. Both of them are. Their power source, a small nuclear generator that has been slowly losing its heat since the day they launched, is running down. Every year they have less energy available. Every year, mission engineers have to shut off another instrument, another subsystem, another feature, in order to keep the essential ones alive. In 2024 and 25, engineers have been performing what can only be described as delicate long-distance surgery on both spacecraft, shutting down instruments and rerouting power, trying to squeeze another year, another 2 years, another 5 years out of them. But the arithmetic is unforgiving. Sometime in the late 2020s or early 2030s, one by one, the last instruments will go dark. The last transmitters will fall silent, and the Voyagers will drift on forever in the interstellar night, no longer speaking to us, no longer being heard. But before that silence falls, they are still telling us things. They are still measuring. They are still, at this very moment, sending back readings that no other human instrument in the universe can send. And those readings, as you are about to hear, describe a region so strange, so counterintuitive, so unlike what anyone predicted, that we are still, more than a decade after the first crossing, struggling to fully understand what they mean. So before we drift on, let me ask you something personal. Think about your own life for a moment. Think about the year you were born. Now think about the fact that in 1977, before many of us were even alive, 2 small human-made spacecraft began a journey that is still going on tonight. Still, at this very second, reporting back to us. What is something in your own life that has quietly persisted, year after year, longer than you ever expected it to? A friendship, perhaps, a habit, a dream, something that started small and just kept going. And when you think of the Voyagers drifting outward for nearly half a century, still whispering across the darkness, does it change how you think about the quiet, persistent things in your own life? Sit with that for a moment. Because now we are going to step through the door that Voyager 1 opened. We are going to cross the heliopause together. And what waits on the other side is a place hotter than any furnace and colder than almost anything you can imagine, both at once. When Voyager 1 crossed the heliopause in August of 2012, mission scientists back on Earth watched their data streams with a strange mixture of excitement and confusion. Because among the many things they had predicted might happen at that boundary, one thing they had not fully prepared for was a temperature reading. And when the temperature reading came back, it was, by any ordinary human standard, impossible. The region just outside the heliopause is hot, blisteringly hot. Somewhere between 30,000 and 50,000 degrees Kelvin. That is hotter than the surface of the sun. That is hotter than a lightning bolt. That is hotter than almost anything you have ever encountered in your life or ever will. And it wraps around our solar system like a superheated skin, a wall of fire at the outer edge of our home. This region has come to be informally called the Wall of Fire, and when you first hear about it, your mind naturally recoils. How can this be? How can the very edge of our tidy little solar system, the border we have to cross to reach the stars, be an inferno hotter than the surface of the sun itself? Would Voyager 1 not simply melt? Would she not evaporate the moment she touched it? She did not. She sailed through it without damage. She sailed through it as if it were not there at all. And she is still, 12 years later, drifting deeper into it, transmitting steadily, her aluminum skin cold to the touch. And here is where you have to abandon everything your senses have taught you about heat. Because temperature, as it turns out, is not the same thing as warmth. When you feel the warmth of a fire, or the heat of a summer afternoon, or the burn of a stove, what you are actually feeling is the transfer of energy from a large number of fast-moving particles to your skin. Trillions upon trillions of molecules of air, or wood smoke, or metal, banging against your nerve endings, dumping their energy into you all at once. It feels hot because so many particles are moving so quickly, all around you, all delivering their tiny packets of energy to your body in the same moment. But out at the edge of the heliopause, the particles are indeed moving fast, extraordinarily fast. Fast enough to correspond to a temperature of tens of thousands of degrees. Yet there are almost none of them. The interstellar medium out there is so thin, so diffuse, that you might have only a single particle per cubic centimeter of space. A tiny sprinkling of atoms drifting through an unimaginable emptiness. And when a spacecraft passes through such a region, so few of those hot particles actually make contact with her metal skin that they cannot warm her at all. She is bombarded, yes, but she is bombarded so sparsely that she loses more heat to the cold of empty space than she gains from the passing particles. Think of it this way. Imagine standing in a completely dark room and someone flicks a single spark across the room toward you. The spark is thousands of degrees hot, but it is one spark. It does not warm the room. It does not warm your skin. It hisses past and disappears. Now imagine that instead of one spark, there are 10 sparks per second drifting through the room. The room is still cold. You still feel nothing. That is what the Wall of Fire is like. A place where the particles are individually blazing, but so few in number that they cannot heat what passes through them. So Voyager 1 is inside a region hotter than the sun's surface, and yet she is deeply, achingly cold. The very concept of temperature loses its intuitive meaning out there. Heat without warmth, fire without burning. A paradox that only makes sense when you begin to think about the universe not in terms of what you can feel, but in terms of what is actually there. And the Wall of Fire is only the beginning of the strangeness. Because just past that hot, diffuse region, the interstellar medium reveals more of itself. And what it reveals overturns another one of our assumptions. For decades, before we crossed the heliopause, Most models assumed that the space just outside our bubble would be relatively empty. Perhaps a few atoms per cubic centimeter, perhaps even less, perhaps a smooth, sparse ocean of near-nothingness. But Voyager 2, with her still-functioning plasma instrument, told a different story. The gas of charged particles out there is more than 40 times denser than the gas just inside the heliopause. Not empty, not sparse, substantial, present, a real measurable physical medium wrapping around our bubble like the surface of a pond wrapping around a bubble of air pushed up from below. And this discovery, quiet and technical as it sounds, has profound implications. Because it means that our bubble is being pressed on from outside by something more forceful than we had assumed. The interstellar medium is not passively yielding to the solar wind. It is pushing back. It is squeezing. It is shaping the outer skin of our home in ways we are only beginning to understand. Then there is the magnetic field. And this is where things get truly strange. Every star, including ours, drags its own magnetic field out with it as it moves through the galaxy. The heliosphere is not just a bubble of gas. It is also a bubble of magnetic field lines, tangled and looping through the region carved out by the solar wind. And beyond the heliopause in interstellar space, there is another magnetic field, the magnetic field of the galaxy itself. A field that has been shaped over billions of years by countless supernovae, by the rotation of the galactic disk, by the movements of gas clouds larger than the solar system, by many orders of magnitude. Before Voyager 1 crossed, scientists expected that when she measured the interstellar magnetic field, it would be pointed in a completely different direction from the Sun's field. That was the whole idea. That was one of the 3 signatures that would tell us she had crossed. But the direction did not change. She crossed, and the field remained pointed nearly the same way as before. And this was so surprising that for months, some scientists wondered if she had really crossed at all. Eventually, they realized what was happening. Near the heliopause, the interstellar magnetic field is being deformed, draped, pushed around. It is like the flow of a river bending around a stone. Our bubble is the stone. The galactic magnetic field is the river. And near the boundary, that field is forced to conform to the shape of our bubble, so that its direction close to our heliopause happens to match, roughly, the direction of our own field just inside it. Only farther out, deeper into interstellar space, does the true undisturbed galactic field reveal its natural orientation. Voyager 1 is still, to this day, drifting through the transition zone, still measuring the slow, gradual turning of the field around her, still telling us, bite by bite, transmission by transmission, how our little bubble bends the great magnetic weather of the galaxy around itself. And then there are the cosmic rays. Inside the heliosphere, the flood of high-energy particles from deep space is suppressed. Our bubble deflects them, scatters them, blocks a significant fraction of them from ever reaching the inner solar system. But once you cross the heliopause, that shield falls away, and the full cosmic ray environment of interstellar space reveals itself. When Voyager 1 crossed, her cosmic ray detectors surged. Almost overnight, she was being bombarded by roughly twice as many of these ultra-high-energy particles as she had been just before. These are not the gentle particles of the solar wind. These are protons and heavier atomic fragments accelerated to nearly the speed of light by supernovae explosions thousands or millions of light years away, drifting through the galaxy for eons before finally reaching our neighborhood. They carry enormous energy in each individual particle. They can pass through metal, through rock, through flesh. They are, quite bluntly, the reason that any long-term human presence in interstellar space would require radiation shielding beyond anything we can currently build. And here is the sobering truth. Every second of every day, our heliosphere is deflecting a significant fraction of those particles away from Earth. Not all of them. Some still make it through. Some reach our upper atmosphere and shower down as secondary particles that trigger radiation counters at ground level. Some pass through our bodies right now, this very moment, leaving tiny trails of damage in our cells that our biology quietly repairs. But without our bubble, without our sun's endless outward wind, that flood would be roughly twice as thick. The genetic damage across the tree of life would be greater, the mutations more frequent. The evolution of complex life on Earth might have taken a different path, or perhaps no path at all. We do not think of ourselves as being sheltered by an invisible bubble. We do not feel it, we cannot see it, and until recently we could barely even measure it. But Voyager 1 and Voyager 2 have shown us, in the plainest possible terms, that the shelter is real, that there is a distinct inside and a distinct outside, that our solar system has a skin, and that skin does something important, something protective, something quiet and constant and utterly essential to who we are. Remember, at the start of all this, the tidy diagram from your childhood. 8 little planets in concentric rings on a black background. That diagram never once mentioned that we live inside a hot, thin, magnetic bubble. It never showed the wall of fire at the edge. It never hinted that just beyond that wall, the density of matter jumps by a factor of 40. It never suggested that our star bends the galaxy's magnetic field around us like a stone bending a stream. All of that was invisible to us, unknown to us, missing from every classroom poster and every textbook, until 2 small spacecraft, drifting for 4 decades, finally reached the edge and touched it with their instruments and whispered the truth back to us. But even now, even with everything the Voyagers have taught us, the story of what surrounds our bubble is not finished. Because in 2009, a different NASA mission, one that never left low Earth orbit, made a discovery about the outer skin of our heliosphere that no model had predicted. A discovery so strange, so unexpected, that scientists have been arguing about its meaning ever since. A discovery that looks from a distance like a great glowing band wrapped around our entire solar system, painted on the inside surface of the wall of fire itself. So before we go there, before we look at that ribbon, I want you to sit for a moment with the paradox we have just uncovered. There is a place, out at the edge of your solar system, that is simultaneously hotter than the sun's surface and colder than almost anywhere you can imagine. A place where fire and freezing exist in the same breath of space. And it made me wonder, have you ever felt something similar in your own life? A moment or a memory that carried two opposite feelings inside it at the same time. A joy that was also a grief. A warmth that was also a loneliness. Something intense but sparse, filling you and yet leaving you empty. Take a moment with that, because now we are going to look at something even stranger than the wall of fire, something that appears to be painted on it. Something that no one in any model, in any theory, ever predicted would be there at all. In 2008, NASA launched a small spacecraft into orbit around the Earth. She was not a Voyager. She was not going anywhere. She would spend her entire working life circling our planet at a distance of only a few tens of thousands of kilometers. She weighed less than 150 kilograms. She was, by the standards of great planetary missions, modest, quiet, almost forgotten by the general public before she even reached orbit. Her name was the Interstellar Boundary Explorer, and most people called her by her initials, IBEX. Her mission was strange. She was not going to fly to the edge of the solar system. She was not going to take pictures of another world. She was going to sit in Earth orbit, and she was going to look outward. Outward in every direction. Outward at nothing that any ordinary telescope could see, because IBEX was not a telescope in the traditional sense. She did not detect light. She detected something else, something no one had ever tried to make a map of before. She detected energetic neutral atoms, individual atoms, mostly hydrogen, that had been born out at the edge of the heliosphere in a series of complicated interactions between the solar wind and the interstellar medium, and that had then drifted quietly back toward the inner solar system, back toward the sun, back toward Earth, where IBEX was waiting to catch them one at a time. Every atom she caught was a message, a tiny particle carrying information about the place where it had been born. If IBEX caught many atoms from one direction and few from another, that told her something about the shape and behavior of the heliopause in those directions. In effect, she was building a picture of our bubble's outer skin by listening to the whispers of individual atoms drifting home. It was patient work. It was slow work. It required years of collecting to build up even a single complete map of the sky. And when the first map was ready in October of 2009, and the science team unveiled it to the world, they were confronted with something none of them expected. There, painted across the sky, wrapping partway around our solar system, was a bright, glowing band, a stripe, a ribbon. It came to be called, quite simply, the ribbon, and it was and remains one of the strangest features ever discovered in the outer solar system. The ribbon is a narrow arc of unusually bright, energetic neutral atom emission. It stretches across the sky in a curve, wrapping partway around the direction of our motion through the galaxy. Along that arc, IBEX was catching 2 to 3 times as many atoms as she was catching from any other region of the sky. The rest of the map showed a smooth, gradual, roughly uniform glow, exactly what the models had predicted. But the ribbon was not in the models. The ribbon was not in the theory. The ribbon was not supposed to be there at all. And here is the truly humbling part. When IBEX launched, dozens of research groups around the world had built detailed computer simulations of what she should see. Some of those simulations were extraordinarily sophisticated, running on some of the largest supercomputers of the time, incorporating decades of research into how the solar wind interacts with the interstellar medium. Not a single one of those simulations predicted a ribbon. Not one. When the map came back, every model was wrong. Every prediction had missed the most striking feature in the sky. For the scientists involved, this was both thrilling and unsettling. Thrilling, because it meant there was a real discovery to be made. Unsettling, because it meant that our understanding of the outer heliosphere was incomplete in some fundamental way. Something was happening out there at the edge of our bubble that our best theories had not accounted for. Some process, some structure, some interaction between our star and the galaxy was producing a bright glowing band that we had not known to look for. In the years since, scientists have proposed a number of possible explanations. The leading hypothesis, refined over more than a decade of analysis, involves something called the secondary energetic neutral atom mechanism. It goes something like this. Out beyond the heliopause, in the region we have been calling the wall of fire, particles from the sun and particles from the galaxy are constantly interacting. Some solar wind particles, having drifted outward and crossed the heliopause, undergo a series of exchanges with interstellar hydrogen atoms, in which they trade electrons back and forth. In these exchanges, some particles briefly become neutral, and a neutral particle is no longer bound by magnetic fields. It flies in a straight line, wherever its momentum was carrying it in that instant. Under normal conditions, these neutral particles fly off in all directions, producing that smooth, uniform glow the models had predicted. But in one special region, the geometry of the interstellar magnetic field just outside our bubble is such that the neutral particles are preferentially produced along a narrow arc. Wherever the interstellar magnetic field lines are perpendicular to our line of sight, an unusually bright glow appears. And that glow, wrapping partway around the sky, is the ribbon. If this hypothesis is correct, then the ribbon is not really a physical structure out there in space. It is a projection. It is the visible signature of the way the galactic magnetic field drapes over the outside of our bubble. It is a shadow, a trace, a map painted on the sky of a magnetic geography we cannot otherwise see. But even this hypothesis, elegant as it is, does not explain everything. Because the ribbon has been observed to change over time, it grows brighter, it grows dimmer, it shifts subtly in position, and it appears to respond with some delay to changes in the activity of the sun itself. When the sun is more active, the ribbon behaves one way. When the sun is quieter, it behaves another. The interior of our bubble, in other words, is communicating with its outer skin. The sun is sending signals outward at the speed of the solar wind, and those signals, taking many years to arrive, are subtly changing the shape and brightness of a feature painted on the far side of the heliopause. It is as if our star is quietly writing on the wall of its own bubble, and Ibex is reading the writing back to us. There are still, at this moment, unresolved questions about the ribbon, whether it is entirely magnetic in origin or whether some other physical process contributes. Whether there might be additional structures like it that we have not yet mapped in detail. Whether the ribbon connects to phenomena inside the Heliosphere that the Voyagers detected in their own crossings. Some scientists have even proposed that certain unexplained particle bursts detected by the Voyagers during their long drift through the outer heliosphere might be related to the physics that also produces the ribbon. If so, then two completely different types of instruments, in two completely different locations, have caught glimpses of the same underlying process and are quietly agreeing that something is happening out there that we do not yet fully understand. Ibex is still working. She is still in orbit. She is still, as you listen to this, adding to the map, filling in more detail, watching the ribbon evolve year by year. In more than a decade and a half of continuous observation, she has produced the most complete picture of the outer boundary of the heliosphere that humanity has ever assembled. And that picture, quiet and abstract as it is, has fundamentally changed the way scientists think about our place in the galaxy. But Ibex is old now. Her instruments are aging. And even before she reaches the end of her useful life, NASA has been preparing her successor. A spacecraft called the Interstellar Mapping and Acceleration Probe, or IMAP. IMAP is much larger than Ibex. She carries 10 instruments instead of 2. She is designed not just to map the outer heliosphere in exquisite detail, but also to study the solar wind, the acceleration of energetic particles, and the interstellar dust drifting into our bubble from the galaxy beyond. And she is being sent not to Earth orbit, but to a special point in space about 1.5 million kilometers from Earth, in the direction of the Sun, where she can watch the outer boundary of our home continuously, without interruption, for years on end. IMAP launched into space in September of 2025, and by early 2026, she has been arriving at her operational post and beginning her mission of observation. In the years ahead, she is expected to give us a picture of the heliopause and the ribbon at a level of detail that Ibex could only dream of. She may finally settle some of the questions that have hung over the ribbon since 2009. She may reveal new features that no one has yet imagined. She may, once again, catch our best theories flat-footed, forcing us to rewrite our understanding of our own outer skin. Because that is the pattern that has emerged, again and again, in the last 20 years of interstellar boundary research. Every time we send a new instrument to study the edge of our bubble, we find something we did not expect. The Voyagers found a wall of fire we could not fully explain. Ibex found a ribbon no model predicted. And now IMAP, in the years just ahead, will almost certainly find something else. Something none of us has yet guessed at. And this is a humbling thing to sit with. Because for centuries, we have imagined that our own solar system was the part of the universe we understood best. The near sky, the home neighborhood, the place where our theories were tested and confirmed, the place where surprises should be least likely. And yet, at its very outer boundary, only a few dozen light hours from the sun, we keep finding things we did not know were there. A hot skin, a dense outer medium, a ribbon painted on the sky by invisible magnetic geography. Whole regions of physics still hidden from us in our own backyard. It makes you wonder what other quiet, unexpected features are waiting for us just a little further out, or maybe just a little closer in. Or maybe, in some sense, hiding in plain sight, in features of the sky we have been looking at for centuries but never quite understood. Now, before we drift onward, sit with this for a moment. Ibex was not sent to find anything specific. She was sent to look, patiently and openly, at a boundary no human eye could see. And when she looked, she found something that no one had predicted at all. And that discovery has quietly reshaped our understanding of our own home. So I want to ask you something. When was the last time you truly paid open attention to something in your own life, without expecting anything in particular from it? Just watched, or listened, or noticed. And did you find something unexpected there too? Some small, quiet ribbon of your own life that you had never noticed before, painted across your days, waiting to be seen. Sit with that. Because in a moment, we are going to step back even further, and we are going to look at the shape of our bubble itself. And what we have been drawing on our diagrams for decades, as it turns out, may be one of the most persistent and misleading pictures of all. For as long as astronomers have drawn pictures of the heliosphere, they have drawn it the same way. If you have ever seen a scientific illustration of our solar system's outer boundary, you have almost certainly seen it in the shape of a comet. A rounded, blunt front, a long, tapering tail. A structure something like a raindrop or a bullet, moving through the galaxy, pushing against the interstellar medium ahead of it and trailing a long wake behind. The reasoning behind this shape was intuitive, elegant, and for many decades almost universally accepted. Our sun is not stationary. It is moving through the galaxy, orbiting the center of the Milky Way at more than 200 kilometers per second, carrying our entire solar system along with it. And relative to the local interstellar medium, our sun is drifting at about 26 kilometers per second in a specific direction. As it moves, it should be running into the interstellar material ahead of it, compressing that material into a rounded front, and leaving a long tail of trailing solar wind behind. Just as a fast-moving raindrop pushes air aside in front of it and leaves a wake behind, our solar bubble, moving through the galaxy, should have a distinct nose and a distinct tail. This picture has been in textbooks for decades. It has appeared in NASA press releases. It has been drawn on classroom posters and in encyclopedias, and in countless documentaries. Every serious diagram of the heliosphere, up until recently, has shown some version of a comet-shaped bubble drifting through the darkness, with a long tail streaming out behind it, sometimes stretching for many hundreds or even thousands of astronomical units into the interstellar night. And yet in the last decade, that picture has come under serious question. Because as more data has come in from the Voyagers, from IBEX, from the Cassini spacecraft at Saturn, and from the New Horizons spacecraft as it flew past Pluto and beyond, the neat comet shape has begun to unravel. The measurements have refused to line up with the tidy raindrop diagram, and in its place, several competing new shapes have been proposed, shapes that are stranger, shapes that are more complex, shapes that, if any of them turn out to be correct, would mean that almost every diagram of the heliosphere ever drawn is fundamentally wrong. The first serious cracks in the comet picture came, of all places, from Cassini. Cassini was a large NASA spacecraft that spent 13 years orbiting Saturn, from 2004 to 2017. She was not designed to study the heliosphere. She was designed to study Saturn, its rings, and its moons. But she carried an instrument that could detect energetic neutral atoms, similar in principle to what IBEX would later use. And from her vantage point in the outer solar system, that instrument could see something that IBEX, in Earth orbit, could not see quite as well. It could see the direction of our motion through the galaxy, and it could see the opposite direction, the direction of the supposed tail. And when Cassini looked toward the tail, she saw something surprising. The tail was not clearly there. The distribution of energetic neutral atoms did not show the strong asymmetry that a long comet tail should have produced. Instead, the sky behind our direction of motion looked, in her data, almost as bright as the sky in the direction of motion. Not identical, not perfectly symmetrical, but surprisingly similar, surprisingly rounded, not the shape of a comet at all. This was startling, and it led some scientists to propose a radical alternative. Perhaps our heliosphere does not have a long tail. Perhaps it is much rounder than we thought. Perhaps it is, in some sense, almost bubble-shaped in the truest meaning of the word, with only a modest asymmetry between the front and the back, rather than the dramatic tapering tail we had drawn for generations. Then came another proposal. This one came from a group of scientists using computer simulations that included effects that earlier simulations had left out. When they added in the fine details of how the solar magnetic field twists and loops through the outer heliosphere, and how it interacts with the interstellar magnetic field just outside the boundary, the resulting shape of the bubble did not look like a comet at all. It looked in their models almost like a croissant. A croissant, a shape with two lobes curving away from each other, connected in the middle, with the whole structure being much more compact than a long-tailed comet would suggest. If this simulation was correct, then our heliosphere would extend only a few hundred AU in any direction, with the two lobes on the flanks and a compact structure toward the tail, rather than the enormous streaming wake we had long imagined. Not everyone agreed. Other scientists, using different modeling approaches, continued to argue for versions of the classical comet shape, perhaps with modifications, perhaps with a shorter tail, but still fundamentally elongated. Still other groups proposed compromise shapes, somewhere between the croissant and the comet. And what emerged over the last several years has been an active, ongoing scientific debate about the true shape of our own home. a debate that, remarkably, has not yet been resolved. Meanwhile, out at the edges of the solar system, other spacecraft were quietly contributing their own pieces of evidence. New Horizons, the spacecraft that gave humanity its first close-up view of Pluto in 2015, has continued outward, into the region beyond the Kuiper Belt. She carries an instrument that measures the density and behavior of interstellar dust particles drifting into the solar system from outside. And her measurements have been telling scientists something subtle but important about how the outer heliosphere interacts with the material of the galaxy around it. Every observation from New Horizons, every additional data point, has been fed into the debate, refining the models, sharpening the picture, but not yet fully settling the question. And here is what makes the situation so remarkable. Right now, in this decade, we do not know for certain what shape our own solar system's outer boundary has. We do not know how far the tail extends, or whether there is a tail at all. We do not know whether our bubble is rounded or croissant-shaped or something in between. We do not know, with confidence, one of the most basic geometric facts about our own home. And this is not a matter of ignorance in some abstract corner of astronomy. This is a matter of ignorance about the very shape of the region in which we live. There is something humbling about this, and there is something wonderful about it too, because it means that even now, after decades of space exploration, our home is still capable of surprising us, still capable of hiding its true form from us, still capable of forcing us to admit that our tidy diagrams have been, all along, best guesses, approximations, sketches drawn by people who had never actually seen what they were sketching. The IMAP mission, now beginning its work, is expected to make major contributions to resolving these questions. With 10 instruments and a stable observing position, IMAP will be able to build far more detailed maps than IBEX ever could. She will be able to distinguish subtle features in the energetic neutral atom distribution that will help scientists decide between competing shape models. She will be able to track changes in the outer heliosphere over time with much greater precision. And she will, in all likelihood over the coming years, help us settle at least some parts of the great question of what shape our home actually has. But even before IMAP delivers her final verdict, one thing has already become clear. The old diagram was wrong. The classic comet shape, with its long tapering tail streaming out behind, was probably an oversimplification at best, and an outright misrepresentation at worst. The true shape of the heliosphere is stranger, more complex, and more interesting than anyone had drawn. It is a shape shaped by magnetic forces we can barely picture, a shape sculpted by the interaction between our star's outward wind and the invisible fields of the galaxy, a shape that changes as the sun's activity rises and falls over its 11-year cycle, a shape that breathes and shifts and does not sit still, and this leads to an even deeper realization. The heliosphere is not a fixed object. It is a dynamic, living structure. It expands when the sun is more active and contracts when the sun is quieter. Its outer skin ripples in response to gusts and lulls in the solar wind. Its tail, If it has a tail, twists and coils as it responds to changes in the interstellar magnetic field. Its shape at any given moment is a snapshot of an ongoing conversation between our star and the galaxy around it. A conversation that has been going on for 4.5 billion years and will continue for billions of years more. Think for a moment about what this means. The place where you live, this bubble, this shelter, this vast invisible cathedral of our sun's making, has never been the same shape twice. Every day, in tiny ways, it is different from the day before. Every century, in larger ways, it has been different from the century before. And every million years, in truly dramatic ways, it has responded to the galactic environment through which our sun has been drifting. The bubble that shelters you tonight is not the same bubble that sheltered the dinosaurs. It is not the same bubble that will shelter whatever creatures walk the earth a million years from now. It is a slowly evolving structure, constantly rebuilt by the wind of our star, constantly reshaped by the pressure of the galaxy. And remember, at the very beginning, that flat diagram from your childhood. 8 planets in 8 tidy circles on a static black background. Nowhere in that diagram was there any hint that our solar system had a shape at all. Nowhere in that diagram was there any indication that its true form was contested, or dynamic, or unknown. Nowhere in that diagram was there room for a debate about whether our home is more like a raindrop, or a croissant, or something else entirely. The diagram gave you certainty. Reality has given us mystery. Now, before we drift further outward, there is one more thing worth sitting with. The comet shape idea persisted for decades, largely because it made intuitive sense. We had all seen raindrops. We had all seen the shape of things moving through a medium. So we drew our bubble in the shape that seemed obvious. And for a long time, no one thought to seriously question it. Which makes me wonder, what beliefs about your own life have you carried for years simply because they seemed obvious? What mental pictures of your own circumstances, of your own relationships, of your own possibilities, have you accepted without checking? And when was the last time you allowed yourself to consider that the shape of things might be quite different from what you had always assumed? Sit with that question for a moment, because now we are going to step back even further and we are going to look at what our little bubble, whatever its exact shape may be, is drifting through. And it turns out our bubble is not floating in empty space at all. It is moving through a much larger structure, a structure that has been quietly shaping our sun's journey for the last 60,000 years. There is a story we have not yet told about our solar system, a story that has nothing to do with the sun or the planets or the heliosphere itself. A story about where we are, not in the sense of our address in the galaxy, not in the sense of which spiral arm we happen to be passing through at the moment, but in a much more intimate sense. What we are surrounded by, right now, tonight, in the region of interstellar space just outside our bubble. What is out there? What we are drifting through. For a long time, astronomers assumed that the space between the stars was more or less uniform, thin, cold, sparse, perhaps with some variation from place to place, but broadly the same everywhere. a featureless emptiness, punctuated by the occasional dense cloud of gas and dust, but otherwise unremarkable. The space between the stars was, in the imagination of most people, just a background, just a stage on which the stars performed, not itself worthy of much attention. But over the last several decades, and especially in the last 20 years, that picture has been slowly, painstakingly revised. And what has emerged is astonishing. The space between the stars is not uniform. It is not featureless. It is not a background. It is a landscape. A vast, complex, three-dimensional landscape of clouds and cavities and streams and boundaries, sculpted over hundreds of millions of years by the violent lives and deaths of stars. And our sun, carrying its little bubble, along with it, is drifting through this landscape at 26 kilometers per second, moving from one cloud to another over spans of tens of thousands of years, weaving its way through a structure so vast that we have only recently begun to map it. Right now, at this very moment, our sun is embedded in a small cloud of thin, warm gas called the local interstellar cloud. Sometimes astronomers call it the local fluff, which is a charming name for something so profoundly important. The local interstellar cloud is not a dense object. Its density is barely enough to register as any kind of gas at all by earthly standards. Perhaps a tenth of an atom per cubic centimeter, or somewhere in that neighborhood. To your senses, it would be indistinguishable from a perfect vacuum. But over the enormous distances of interstellar space, even that tiny density adds up. It is real. It is measurable. It is there. The local interstellar cloud is somewhere around 30 light-years across. Our sun entered it somewhere between about 40,000 and 150,000 years ago, in the middle of the last ice age, when our ancestors were still hunting mammoths across the tundra. Before that, our sun was drifting through slightly different material, with slightly different properties. And in the not-too-distant cosmic future, in perhaps another 10,000 to 20,000 years, our sun will drift out of the local interstellar cloud entirely, and into whatever region lies on the other side. Take a moment with that. The cloud we are currently drifting through is not permanent, at least not on the scale of our sun's journey. Our star, on its long orbit around the galactic center, is passing through it the same way a ship passes through a patch of fog. On a human timescale, nothing changes. On the scale of an ice age, everything might be different. Our great-great descendants, if any of them are still around in 20,000 years, will look up at a night sky that is subtly different from the one we see tonight. The interstellar weather around our sun will have changed. The pressure on our heliosphere will be different. The precise shape of our bubble may be somewhat altered. The rate of interstellar dust drifting into our solar system may be higher or lower than it is today. And this is only the smallest layer of the landscape, because the local interstellar cloud is itself sitting inside a much larger structure. A structure that is so big and so quiet and so long ignored that it has only truly come into focus in the last decade or two of astronomy. Our solar system and the local interstellar cloud and a number of neighboring interstellar clouds, are all sitting inside an enormous cavity in the galactic gas. An immense, roughly bubble-shaped region where the interstellar medium is far thinner and hotter than the average of the galaxy. This cavity is called the local bubble, and it is about 1,000 light-years across. Try, if you can, to picture that. Our heliosphere, which we have been calling vast, and which is indeed vast by any standard involving planets or human distances, is only about 1/300,000th of a light-year across at its outer edge. And this local bubble that surrounds us is 1,000 light-years across. Our heliosphere is to the local bubble what a grain of sand is to a football field. Our bubble is inside a much larger bubble, and that larger bubble is what our sun has been drifting through for at least the last several million years. The local bubble was not always there. It was carved out. It was made. It was hollowed into the gas of the galaxy by a series of enormous explosions, spanning perhaps 15 million years, in which somewhere between 14 and 20 massive stars, in the neighborhood of our current position, ended their lives in supernova explosions. Each of those explosions blasted immense quantities of hot gas outward in all directions, pushing the surrounding interstellar medium into a thin, expanding shell, and leaving behind a vast, hot, low-density cavity in the middle. Over the course of about 15 million years, the combined effect of all those supernovae was to sweep out an enormous, roughly spherical region of relatively empty space, with a thick shell of compressed gas around it, in which new stars have since been forming. And our sun, along with the small cloud we are currently drifting through, is inside that cavity, right in the middle of it, not because our sun was born there. Our sun is much older than the local bubble, roughly 4.5 billion years old, and has drifted into the region on its long orbital wandering. But now, for this stretch of our journey, we happen to be sitting inside the aftermath of an ancient set of stellar deaths. The stars that died to make the local bubble have been dead for millions of years. Their shells of expelled matter have dispersed. Their contribution to the galaxy is 1,000 light-year cavity of thin, hot gas, and we are floating in it. The realization that we live inside such a bubble has only truly matured in the last several years. Detailed maps of the local bubble, using data from the European Space Agency's Gaia mission, which has measured the precise distances to more than 1 billion stars, have allowed astronomers to trace the boundaries of the cavity with unprecedented precision. And those maps have revealed something even more striking. Almost every young star-forming region within about 500 light-years of our sun is sitting on the surface of the local bubble, not inside it, not scattered randomly, but on the compressed shell of gas at its outer edge, where the ancient supernova blast waves piled up interstellar material and triggered new waves of star formation. The local bubble, in other words, is a nursery. The deaths of ancient massive stars carved out a cavity, compressed the surrounding gas into a shell, and then that shell has been giving birth to new stars for millions of years. Almost all the nearest star-forming regions to our sun, including the well-known ones in Taurus and Ophiuchus and Chameleon and elsewhere, are riding the surface of this vast, invisible, ancient wound in the galaxy. A wound that has become a womb, and we are in the middle of it. Take that in for a moment. The nearest star-forming regions to us, the places where new suns and new planets are being born tonight, are all sitting on the shell of a cavity that was carved out by the deaths of stars that lived and died millions of years ago. The ancient dying stars pushed out the gas. The pushed-out gas became a shell. The shell has been forming new stars. And those new stars will, in their own time, live their lives, and some of them will die in supernovae of their own, and those supernovae will carve their own cavities and push their own shells, and trigger their own next generation of star formation. It is a cycle. A vast, slow, generational cycle in which the deaths of stars fertilize the births of stars, and the shape of the galaxy at any given moment is a snapshot of countless such cycles overlapping. Beyond the local bubble in every direction are other bubbles, other cavities, other structures carved out by other supernovae in other times. Astronomers have mapped several of them in recent years, and they connect and overlap and touch in complex ways, forming a kind of foam of interstellar structure that extends throughout the disk of the Milky Way. Our galaxy, at the scale of interstellar clouds and cavities, is not a smooth thing. It is porous. It is bubbly. It is a vast, intricate froth of ancient explosions and their aftermaths, drifting slowly around the galactic center over hundreds of millions of years. And within this froth, our little sun, with its little bubble, is a single tiny bead. A bead currently sitting inside the local interstellar cloud, which is inside the local bubble, which is one bubble among many, which are all inside the larger structure of the Orion arm of the Milky Way, which is itself only one arm of a great spiral galaxy of hundreds of billions of stars. Layer upon layer of context, each of which our childhood diagram never mentioned, each of which we live inside without seeing. There is one more piece to this story, and it is a piece that only recently has come into serious scientific view. Some astronomers have been asking whether our sun's slow drift through this landscape of clouds and cavities might have left traces in the geological or biological record of Earth. There is some evidence, still debated, that when our solar system passes through denser interstellar clouds, the heliosphere may shrink somewhat, exposing the inner solar system to slightly higher levels of cosmic radiation, and possibly changing the influx of interstellar dust into the planetary region. Some researchers have found intriguing signatures of radioactive isotopes in the geological record of the deep ocean floor, isotopes like iron-60, that appear to be signatures of ancient nearby supernovae. Signatures that arrived on Earth millions of years ago, drifted down through the atmosphere, and were incorporated into the sediment. It is as if the deaths of ancient distant stars have left their fingerprints on the seabed of our own world, and this suggests something remarkable. The story of our planet is not, and has never been, purely a local story. It is not just a story of geology and biology and climate and evolution playing out on a single small blue world. It is also a story of what is happening in the interstellar neighborhood around our sun, what clouds we are passing through, what bubbles we are inside, what supernovae have exploded near us in the past, and what supernovae might explode near us in the future. The state of our solar system, and even in small ways, the state of life on Earth, is quietly influenced by the shape and content of the galactic environment we happen to be drifting through. We are not, and have never been, alone in our little bubble. We have always been inside something larger, and that something larger has always quietly been influencing us. Now, before we take the final step of our journey together, sit with that for a moment. Every star you see in the night sky is drifting through the same great structure of clouds and cavities and shells that our sun is drifting through. Every one of them has its own bubble, its own patch of local weather, its own moment in the galactic seasons. And they are all changing, all the time, over spans of time so long that no human lifetime could ever perceive it. So I want to ask you something. When you consider that you are riding right now, on a planet that is riding on a star that is drifting through a cloud that is sitting inside a bubble, that is one bubble among many in a great galactic froth, how does that make you feel about the ground beneath your feet? Does it feel more solid or less, more precious or more strange? Take your time with that, because now we are going to take one final step back, one final zoom out, one final moment to look at everything we have seen tonight and to ask, gently, what it all really means. So let us retrace the journey we have taken together tonight, not as a summary, not as a checklist of facts, but as a slow, quiet walk back through everything we have seen before we take our final step. We began with a picture, a tidy diagram from your childhood, a yellow sun, 8 neat planets in 8 neat concentric circles, and a black background pretending to be empty. That was where we started. That was the mental image you had been carrying for as long as you could remember. And then we began to peel it away. We saw that our sun is bleeding, silently and constantly, from every point on its surface. That its outward wind carves a vast bubble around itself. A bubble so large that all of the planets, all of the moons, all of the asteroids and comets, all of the spacecraft ever launched, and every human being who has ever lived, all sit inside it. We called that bubble the heliosphere, and we saw that its outer skin, the heliopause, sits at more than 100 astronomical units from the Sun, 3 times farther out than Neptune's orbit, at a distance so vast that even light itself takes nearly a day to cross it. We followed 2 small, ancient spacecraft to that edge, Voyager 1 and Voyager 2, 2 machines built in the 1970s on primitive computers, by human hands that could not have imagined how far their creations would travel. We watched them drift outward for 4 decades. We watched them cross the termination shock. We watched them push through the Heliosphere. And then, in 2012 and 2018, we watched them step through the outer skin of our bubble and become, for the first time, human artifacts in interstellar space. We saw what they found there. A wall of fire, hotter than the surface of the sun, so thin that it could not warm anything that passed through it. We saw that heat and warmth are not the same thing. That temperature can be blistering and yet almost imperceptible. That the outer edge of our home is a place of paradoxes, a place where our human senses would tell us nothing, but where our instruments could measure the truth. We saw that the interstellar plasma just outside our bubble was more than 40 times denser than expected. That the magnetic field of the galaxy is bent and shaped by our little home. That the flood of cosmic rays we live under, here on Earth, would be roughly twice as heavy without the invisible umbrella of our star's breath shielding us. That we are, in the deepest sense, children of the bubble, sheltered by it, shaped by it, utterly dependent on it, though we cannot see it, cannot feel it, cannot hear it in the silence of a summer night. We saw the ribbon, that glowing arc across the sky that Ibex discovered in 2009, a feature no model had predicted, a feature that turned out to be, most likely, a map of the interstellar magnetic field draped over the outside of our bubble, a signature of geometry we could not otherwise see. We saw that IMAP, now beginning her mission, will continue this work and will probably surprise us again with something we have not yet imagined. We saw that the shape of our bubble itself is not what we had drawn for decades, not a raindrop, not a simple comet, perhaps a croissant, perhaps something between, perhaps something no one has yet found the right words to describe. We saw that our own home has been hiding its true form from us, and that even now, in the middle of this decade of space exploration, we are not certain what shape the region we live in actually has. And then we stepped back one more layer. We saw that our bubble is drifting through the local interstellar cloud, a small, thin, warm mass of gas that our sun entered somewhere in the middle of the last ice age, and that we will drift out of, eventually, in some slow future our great descendants will inherit. We saw that this cloud, and our bubble and everything within it, is sitting inside the local bubble, a cavity carved out of the galaxy by the deaths of ancient stars, 1,000 light-years across, ringed by the compressed shell of gas from which new suns are still being born tonight. We saw that our neighborhood is a nursery, and that the deaths of distant stars have quietly left their fingerprints in the sediments of our own oceans. Each layer, when we reached it, made the previous layer look small. That is the shape of what we have done together. That is the journey we have taken, from a childhood diagram to a great galactic froth of ancient explosions. From a yellow circle on a piece of paper to a bead of a bead of a bead, nested inside structure after structure, each one older, each one larger, each one older than the last. And now we come to the final question. The question that has been hovering at the edge of everything we have said tonight, waiting patiently for its turn. Where does our solar system actually end? We began with that question. We have circled it. We have approached it from many directions. And now, at the end of our journey, we are ready to see something that we could not see at the beginning, something that changes the question itself. There is no clean edge. There is no wall. There is no fence. There is no line drawn across space with our solar system on one side and the galaxy on the other. There is only a series of gradients, the solar wind fading, the plasma changing density, the magnetic field slowly turning, the cosmic rays gradually intensifying, the interstellar clouds subtly shifting. Every one of these transitions happens over enormous distances. Every one of them blurs into the next. And even the crossings that Voyager 1 and Voyager 2 made, those precise dates in 2012 and 2018, are really just the moments when they crossed a particular gradient at a particular threshold. Cross a slightly different threshold in a slightly different direction at a slightly different time, and the boundary itself is somewhere slightly else. The heliopause is real, but it is not a wall. It is a place where certain things become true and other things become false. It is a place where the ownership of the magnetic field changes hands. It is a place where the character of the plasma shifts, but it is not the place where the influence of our sun ends. The influence of our sun, in the form of its gravity, extends far, far beyond the heliopause. Comets that visit the inner solar system for a few decades and then wander back out into the darkness are still in some sense ours. Held on their long looping paths by the gravitational hand of our star out to distances of many thousands, perhaps tens of thousands of astronomical units. The influence of our sun does not end at the heliopause. It fades, slowly, over regions of space so vast that even Voyager, at her staggering speed, would take tens of thousands of years to cross them. And in the other direction, the influence of the galaxy does not begin at the heliopause. It has already begun long before that, deep inside our bubble. Cosmic rays reach us from the galaxy. Interstellar dust drifts in from the galaxy. The gravitational pull of nearby stars and passing gas clouds shape the outer boundaries of our own solar system's cometary reservoir. The inside and the outside of our home are not cleanly separated. They interpenetrate. They mingle. The line between them is a fiction we drew for the sake of clarity, which means that the question we began with, "Where does our solar system end?" has no clean answer. It is not that the answer is difficult. It is that the question itself, as we asked it at the beginning, was misleading. We were asking for a line. Reality gave us a gradient. We were asking for a moment. Reality gave us a slow, quiet, endless transition. The concept of an outside was always, in some sense, a human invention, a way of organizing our thinking, a way of drawing tidy diagrams, a way of feeling that we understood the shape of our own home, and it served us well for a time. But the truth, as always, is stranger and richer than the tidy version. The truth is that our solar system does not end. It fades. It blends. It merges over vast, slow distances into the galaxy. And the galaxy, in turn, does not begin at the edge of our solar system. It has always been here in some small measure, threading through us, riding the same gradients, sharing the same continuum. We are not separate from the galaxy. We are the galaxy. A local concentration of it. A small, warm, protected pocket of it. A pocket with a star in the middle and 8 planets around that star, and a bubble of solar wind around those planets, and a ribbon painted on the outside of that bubble, and a cloud drifting through. and a cavity carved by ancient supernovae holding it all, and behind that cavity layer upon layer of galaxy stretching out into the immensity. We are not inside the universe. We are of it. Of it in every atom, every particle, every wisp of plasma, every twist of magnetic field, every drift of dust. And you sitting there tonight, listening to a voice through some small device, in some small room on some small planet, you are a piece of that same continuum. The atoms in your body were made in the hearts of ancient stars, before our sun was even born. They drifted through the galaxy for hundreds of millions of years, before finding their way into the cloud that would collapse and become our solar system. They were forged in the same processes that carved the bubbles we live inside. They are, in the truest possible sense, star matter, not metaphorically, not poetically, literally, physically, chemically. Every breath you take, every heartbeat, every thought, is a small ongoing conversation between star-made atoms and the strange emergent property we call consciousness. You are not observing the cosmos from outside it. You are the cosmos, briefly, momentarily, exquisitely aware of itself, sitting in a room, listening to a voice, thinking about the edge of your own solar system, and there is no edge. There is only home fading gently into everywhere else. That is what NASA found ultimately beyond the heliosphere, not just a wall of fire, not just a ribbon, not just a shape, not just a cloud, not just a bubble inside a bubble. They found, and they continue to find, that our solar system is not an object. It is a region. It is a moment. It is a slow-shifting patch of local weather in a vast galactic ocean. And the very idea of an inside and an outside is something we have to gently release in order to see what is truly there. We began tonight with a diagram. We end tonight with a dissolution of that diagram, not a replacement, not a corrected version, a dissolution. A recognition that the diagram was always a sketch, and that reality has never been diagrammable. Before we drift into silence tonight, let me ask you one last soft favor. If this slow, quiet journey has meant something to you, if it has given you a few hours of stillness and wonder, a small like or a quiet subscribe means more than you might imagine. It is a small thing for you. It is a huge thing for a channel like this one. It helps us keep making these long, patient, contemplative journeys for people who find their peace in the depths of the cosmos, late at night, in the quiet hours. And now, one final thought before we say good night. The next time you step outside on some quiet evening and you look up at the stars, remember this. You are not looking up at a ceiling. You are not looking up at the edge of anything. You are looking out into the same continuous fabric that surrounds you, that flows through you, that has always held you. There is no wall between your body and the farthest galaxy. There is only distance. There is only gradient. There is only the slow, gentle fading of one region of the universe into another, and you, standing quietly in the middle of it, part of the fading, part of the flowing, part of the great slow drift of everything. Our little bubble will keep drifting. Voyager 1 and Voyager 2 will keep drifting. The local interstellar cloud will keep drifting. The local bubble will keep drifting. And you and I and every quiet listener tonight will keep drifting too, for a while longer, together. You are safe inside the bubble. The bubble is safe inside the cloud. The cloud is safe inside the cavity. The cavity is safe inside the galaxy. And the galaxy holds you tonight as it has always held you, and as it will hold you gently for as long as you are here. So rest now. Rest under the stars. Rest inside the bubble. Rest inside the cloud. Rest inside the cavity. Rest inside the galaxy. Rest inside the universe. Rest inside yourself. The cosmos is around you. The cosmos is within you. And there is nowhere in all of it where you do not belong. Sleep well under the stars. Good night.